So, we have seen two applications of microwave, namely radar and wireless communication. Let us now come to another application of microwave frequencies, which is satellite communication. Satellite communication became possible in mid 1960s, and after that there has been a tremendous growth in communication satellites, in use of communication satellites, and not only for communication purposes, satellites are used for navigational and other purposes also. Here our discussions will be limited to communication satellites. So, here we show the telecommunication infrastructure using a communication satellite. We can see that this satellite is essentially it is a repeater in space, and then we have terrestrial interfaces, and then through these terrestrial interfaces the traffic in the form of voice, data, video, these are transmitted using an earth station to a satellite, and then the satellite transmits it back to another earth station, and it then comes to the terrestrial interface through which this voice, data, video, these are delivered to the users. In the earlier days, terrestrial microwave links were developed. The range of this type of links were limited because of the curvature of the earth, and to overcome this we required to increase the height of the tower where the antennas are mounted. So, beyond 40-50 kilometers, the tower heights become very large, and therefore, instead of going for single link, the repeaters were used, and in fact the long distance coverage before the advent of satellite communication, one of the major means of providing long distance coverage was through terrestrial microwave links. Although these are used nowadays also, but their usage has become limited after the introduction of satellite. Now, we will see that these satellites, these are put in orbits which are several hundred to several thousand kilometers above the earth's surface, and therefore they can provide coverage to a much wider range. So, coming back to this diagram, the terrestrial interface acts as the first node for information from the user environment. This information is then directed towards the orbiting satellites using RF links, and this information is then amplified and reprocessed at the satellite end, and then is redirected towards the receiving ground station through another RF link. It may be noted that the frequency that we use for transmitting signals from transmitting earth station to the satellite, it is different from the frequency that is used for transmitting signals from satellite to the receiving earth station. And therefore, we have a translation of frequency takes place in the satellite. We will discuss more about it. Now, the orbits in which the satellites are placed, this can be at various heights. We have LEO satellites or low earth orbiting satellites which are around 1000 kilometers. Then we have MEO or medium earth orbit satellites which can range from 5000 kilometer to 12,000 kilometer. And finally, we have GEO, the geostationary orbit, which is about 36,000 kilometer from the earth, and this is in the equatorial plane of the earth. This is called geostationary because in this orbit when a satellite is placed, it remains fixed above a point on the earth's surface, whereas in LEO or MEO type of orbits, the satellite moves with relative to the earth and it is visible from a particular location only for a fixed period of time, and it completes several rotation around the earth in a day, whereas in geostationary orbit the satellite, it moves along with the earth and appears stationary from a point on the earth's surface. These geostationary satellites are extensively used for communication purposes, and this orbit is actually having large number of satellites, and the satellites are placed as close as a degree on this orbit. Now, there are several advantages of communication satellites. As I have already mentioned, the satellite being at a height from the Earth's surface can provide wide coverage, and also this type of communication satellites are useful for coverage in remote areas where terrestrial coverage become difficult. For example, if we have a isolated village in some hilly terrain, it can be covered from satellite. It may be difficult or economically not viable to have terrestrial coverage in the form of fiber or cables being laid and getting such areas connected. In satellite communication has the advantage of distance independent costs. Broadcast costs are also fixed, and it provides such communication infrastructure provides very high capacity and low error rates can be achieved with satellite communication systems. Let us now talk about the satellite communication segments. We generally talk of space segment, which includes the satellite or satellites in orbit and the ground station that provides the operational control of the satellites in orbit. So, the ground station is referred to as tracking, telemetry, command or the tracking, telemetry, command and monitoring station. So, apart from normal communication payload, the satellite also has to have links which has provision for sending commands uplink and telemetry signals downlink. The ground segment of the communication satellite system consists of terminals that utilize the communication capabilities of the space segment. So, in communication space segment, we have the satellites which can provide us communication channels, and the ground segment has terminals which can make use of these channels, and we have different types of ground terminals, like we can have fixed terminals, we can have transportable terminals. Transportable ones can be moved from one location to the other, but when they communicate they remain fixed, whereas mobile terminals, they can communicate with the satellite when they are moving. So, if we look at the basic link parameters in a satellite communication system, we can see that we have channel which is one way link from A to B, A and B are the two earth station. So, a channel actually forms a link from earth station A to B through the satellite, but it is a one way link. A circuit, this terminology used to denote a duplex link, two-way communication from one earth station to another earth station. A half circuit is a two-way link between a earth station to the satellite, and this basic repeating operation in the satellite is performed using a transponder. Now, let us try to see how a transponder works. To some detail, let us try to see how this transponder works. And here comes the need for designing circuitry in the microwave frequency band, because in the transponder we can see we have a antenna, FU is the uplink frequency, then we have a receiver which might consist of band pass filter, LNA, and then we have a down conversion of this frequency to some intermediate frequency by multiplying with a local oscillator, and then the amplification is performed at the intermediate frequency, and after amplification it is up converted to another frequency FD, which is the downlink frequency, and here then it is given to a power amplifier where the signal power is raised to appropriate level for transmission, and then it is transmitted to the earth station located in the ground. Now, these devices, particularly this power amplifier, it must provide enough power so that detectable signals are obtained, and if you remember, the distance for a geostationary satellite was 36,000 kilometer. So, what we require that enough power is transmitted so that the signal can cover this distance and still remain detectable at the ground station. So, this type of transponder, which does the frequency translation only, and of course it amplifies the signal, these are called non-regenerative type. There is another variety of transponder which is called a regenerative transponder. So, after receiving the signal, it is demodulated. The demodulator consists the down conversion unit also, and the local oscillator is connected here. So, after down conversion and demodulation, the signal is given to a baseband processor where it is amplified, error correction is made, it also does coding and many other functions. After that, it is given to a modulator, and by using this local oscillator, it is also modulated and up converted. Finally, this up converted signal from baseband to the desired frequency, this signal will be amplified by the power amplifier, and then it will be given to the antenna for transmission. So, we see that in a regenerative transponder, it is not only the frequency translation from FU to FD, signal actually gets demodulated, then lot of baseband processing is done, it is remodulated and up converted and given to the power amplifier. Now, some of the frequency bands which are commonly used for satellite communications are: a very popular band is 4 to 6 gigahertz band, another band is 12 to 18 gigahertz, which is Ku band, and the other band is 26 to 40 gigahertz Ka band. Many a times the band which are selected for satellite communication based on several consideration, like the attenuation that occurs to the signal because of absorption. So, in fact, we have several low attenuation windows, and usually the frequencies in these windows are preferred for long distance satellite communication. Now, how to determine the power that we require to transmit, say from satellite to the ground earth station. So, this is calculated using link budget calculation, and we outline a simple link budget calculation from Friis formula. And if we consider the small l representing the losses other than free space loss, we have seen that the signal becomes weak when it propagates because of spreading, which we call free space loss. Other than that, there are several other losses, as we have mentioned. There are absorption due to gaseous particle, maybe absorption due to rainfall. So, all these losses are accounted by L. Then this C, usually it is denoted as carrier power. It is equal to EIRP. EIRP is the effective isotropic radiated power and essentially represent the term PT into GT in Friis formula, and then lambda by 4 pi r whole square into GR divided by L. Now, in link budget calculation of satellite, we find out one quantity which is called C by N, carrier to noise ratio, and once we have the expression for C, the carrier to noise ratio becomes this expression divided by K TSB, where K is the Boltzmann constant, TS is the receiving antenna system temperature, and B is the bandwidth. Now, if we express C by N in dB, then we will have EIRP expressed in dB watt minus free space loss in dB. Free space loss will be calculated as 20 log 4 pi r by lambda, then this other losses L in dB, then GR by TS again in dB, and 10 log 1 by K, this will give this figure 228.6, and this bandwidth B to the power minus 1 will give minus 10 log B. So, this is the carrier to noise ratio, and it has to be properly designed so that we get appreciable amount of signal in the ground station, so that the information can be demodulated and decoded from it. So, briefly, this is about the satellite communication, and various microwave components and sources that we have discussed in our earlier lectures, they find use in satellite communication systems. We require very high gain power amplifiers, TWT type of tubes are extensively used in satellite transponder, and also as we go towards higher and higher frequency for satellite communication, we already discussed the limitation that we face, because at higher frequency the free space loss itself become very large, and therefore we need to design very high gain antennas, highly directional antennas to make up for this type of losses. Let us now move on to industrial and medical application of microwaves. We start with industrial application. There are several industrial applications of microwave based on microwave heating, and we know that microwave oven is a very popular commodity nowadays, and it works on the principles of microwave heating of material. Now, apart from that, the other examples where microwave heating is utilized are drying, vulcanization, polymerizing, pasteurizing, sterilizing, etc. So, there are several other application areas where microwave frequency is used. Usually the ISM band frequencies are used for these purposes. ISM is industrial, scientific and medical. A set of frequencies are set aside for doing this type of activities. Some of the typical center frequencies of such applications are 915 megahertz, 2.45 gigahertz, 24.125 gigahertz. So, these are the ISM band frequencies which can be used for industrial application of microwave. So, let us briefly discuss drying. Microwave and conventional heating sources are combined to control the temperature gradient and humidity gradient. Thus, a uniform drying can be achieved, which is quite useful in paper and printing industries. Now, normally when we heat conventional heating, the heat flows from surface where heat is applied to inside the body. But in microwave heating, the whole material may be heated simultaneously both inside and outside, and therefore more uniform heating can be made. Leather and textile industries also rely on microwave heating for its fast heating capacity. Photographic film processing is another application in which microwave heating is used for selective heating. Let us now come to vulcanization. Vulcanized rubber is more durable and has a higher mechanical strength in comparison to natural rubber, and microwave generators such as klystron or magnetron are used. The applicator where the rubber is placed may be standing wave type or travelling wave type. Helix Mindel line are preferred when travelling wave structure is used. The impedance matching device is used to minimize reflection from applicator during the process of curing of rubber. Let us now come to some medical applications. Microwave hyperthermia and microwave ablation are common medical applications of microwave. Use of microwave radiation for heating is rapid and aseptic. So, here we briefly discuss microwave hyperthermia. Microwave hyperthermia utilizes microwave heating to heat up the tumor cells, resulting in rupture of the cell membrane. In such treatments, special purpose antenna is used to deliver controlled dose of microwave signal to the tumor cells. A typical microwave hyperthermia system consists of a microwave source, an applicator and some temperature monitors with control system for power control. It is found to be effective in treatment of malignant brain tumors. Further, such hyperthermia is found to be non-addictive and does not have any side effects. Let us briefly discuss microwave ablation. Unwanted tissue masses such as tumors are removed using microwave ablation. It is also used in cardiology, cosmetic and dental treatments. Typically, sources operating at 915 megahertz and 2.4 gigahertz frequencies are used for microwave ablation, and 50 ohm mesh loads are used. Dielectric properties of cancerous tumor cell may vary considerably, which can lead to significant mismatch between the source and the load, which is an applicator. In such cases, treatment becomes insufficient. Reduction in this mismatch tolerance is an area of active research. So, with this discussion, we come to the end of this module, and in fact, the end of this course. We have covered various aspects of microwave engineering in this course, which is spread over 12 modules, and we have been particularly focusing on the fundamentals, so that after doing this course, the participants will have sufficient background to pursue any higher studies in this area. Now, microwave engineering, although it started long back and it is a very mature engineering discipline, still people are finding lots of new applications in this field, and there are various directions in which microwave engineering is expanding. Because of the huge demands of communication, the emphasis is shifting from lower microwave frequency bands near few gigahertz to millimeter wave frequency bands. And in fact, we said that in 5G communication, fifth generation of wireless communication, millimeter wave communication is expected to play a vital role. It is worth mentioning here that Professor J.C. Bose, way back in 1897, he was contemporary to Marconi, and he carried out experiments which were actually in the millimeter wave band. So, millimeter wave communication systems are expected to become very popular with the advent of 5G systems. Of course, millimeter wave is used in defense and military applications, but large scale use of millimeter wave frequencies will take place if it becomes a successful implementation in 5G technologies. So, apart from millimeter wave, another band which is above millimeter wave and it is in the no man's land between microwave and optics, this is also being explored, and this is called terahertz band of frequencies. Even the basic microwave frequency bands around few gigahertz, these are also extensively in use, and many other devices like initially the processors used to work in the megahertz range. Now almost all processors, be it a desktop processor or a mobile processor, all these processors, they work in the microwave frequency range. Some work in 2 gigahertz, some in 2.6 gigahertz, some in 3 gigahertz. So, when the processor itself works in the microwave frequency band, many associated circuitries, they also need to operate at that frequency band. So, this is another area where the frequency is increasing and the microwave frequencies are finding lot of application. Although we are having very widespread use of microwave frequencies, at the same time excessive use of microwave frequencies, we need to be very cautious about the health and environmental hazards that may happen with the EM waves in the microwave frequencies. So, this is another area where lot of scopes exist, how to provide communication at the same time not posing any environmental or health hazards, any threat of environmental or health hazard. Another area which is related to these microwaves is electromagnetic interference and compatibility, because most of the equipments which operate in the microwave frequency band, they essentially radiate, and therefore interference becomes a major issue. So, this is another direction where lot of activities are there. So, we have seen the industrial application, we have seen application in the field of radar, we have seen application in the field of satellite communication. So, microwave engineering, the knowledge in microwave engineering will be very, very essential to understand all these technologies, and this is why the focus of this course has remained to provide a basic or fundamental understanding on the various principles of microwave engineering. With this, I thank all the participants who have joined in this course, and thank everyone who have provided me assistance in making this video course possible.